Okay, so today we're going to work with solving a variety of equations using our log rules. So far we've learned about 4 log rules. We have the power rule, which allows us to, it's the whole system, sorry. Which allows us to bring down an exponent that has a log in front of it. So that's power rule. We've got change of base formula, which allows us, for most of our calculators, allows us to actually calculate different logarithms inside our calculator. And then we have product rule and quotient rule, which we learned about on Friday. Okay, so in order to do some of our stuff today, we're going to have to be able to create common bases within some of our values. So we're just going to practice that. I want to write all of these as bases of 2. So how do I write 16 with a base of 2? Julie?
2 to the power of 4.
Was that a hand or not a hand? I don't know. She's got it. 2 to the 4. Okay, good. How about 4 squared? Well, let's think about just 4. How do I write 4 as a base of 2? 2 to the power of 2. So if it's 4 squared, then I have 2 to the power of 2 to the power of 2, which gives me, again, 2 to the 4. Okay, this one we could, actually, I think we can just square root 16. That gives us 4, just to start here. And then with 64, I'm going to express this to the exponent 3 over 6. So actually that gives me 64 to the exponent 1/2. Okay, so 4 we already did. We said 4 was 2 to the exponent 2. How about 64? 2 to what exponent? 2 to the 6. And then here I'm applying power rule. So 6 times 1/2 is 2 to the 3. There are many different ways that you could go about calculating this, by the way. And then I add the exponents. So it'll be 2 plus 3 equals 2 to the 5. Okay, these ones are all nice because they're actually even values that go into, like bases of 2 that go into these values, right? Like 64, 16, 4. What about 14? Well, 14's a little bit tougher because 14 doesn't really give us an exact value. Yep.
For 2 to the 5, would you write 3 to the 2 or just leave it at?
Well, this question asks us to express them with a power and base of 2. So we'll leave it as 2 to the 5. Okay, so here's the question. 2 to what exponent gives us 14? And how could I express that, right? So how do I find x here? Yeah, logarithms. So I'm going to log both sides. Okay, this would be the power rule method of solving this, and I get to bring down the x in front. And if I want to express this exactly with a base of 2, I'm actually going to leave my x value just like this. And that means that I can express 14 as a base of 2 if this is my exponent. So remember, the answer is the exponent on 2 that I would need to raise to 2 to get 14. So 14 is equal to 2 to the exponent log 14 over log 2. Okay, and I'm not going to calculate that because then we get decimals and we have to round, so we'll just leave it in exact values. So this is our final solution here.
Where did you get the 2 from?
I'm expressing all of these with a base of 2, and that's what I solved for. I solved for 2 to what exponent equals 14, and I found that 2 to the exponent log 14 over log 2 is equal to 14.
Why can't you plug that in your calculator again?
You can, but I'm expressing it exactly, so plugging into our calculator is just going to give us a decimal. So I'm leaving it in fraction form. Okay, if you check this on your calculator, like if you do 2 to the exponent log 14 over log 2, you should get exactly 14 out from your calculator. Okay, So we're going to use this idea to solve a variety of expressions with common bases and without common bases. So we need to remember, in order to solve some of these, that if I create two things with common bases, in our rule up here, x's are the common bases, but in our expressions here, we're hoping that the bases can become the same value. But if I express two things with the same base, then I know that their exponents must be equal. That's the rule. So if I have 2 to the exponent something equals 2 to the exponent something else, I know those somethings, those exponents must be equal because they both have bases of 2. Okay, so the idea is if I can express things with common bases, I should do that. So for instance, in this question here, I can express 81 as a base of 3. How do I do that? 3 to what exponent equals 81? Okay, so 3 to the 4, and then I'm going to use power rule here, which says that when I have an exponent of an exponent, I multiply. Okay, now because I'm able here to express these with common bases, 3 to the exponent x plus 6 equals 3 to the exponent 4x. What do I know about those exponents now? They must be equal, yes. So 3 to the exponent 10 is only going to be equal to 3 to the exponent 10, right? So I need these exponents to be equal if we're saying that it's a base raised to some exponent and then the same base raised to the other exponent. So I'm using this rule up here, and I'm saying if the bases are the same, then the exponents must also be the same. Okay, and then we're just going to solve here. So x must be equal to 2. How can I check my work?
Plug in 2 from equation.
Okay, so let's check. Is 3 to the exponent 2 plus 6 equal to 81 to the exponent 2? That's the question. Is 3 to the 8 equal to 81 to the exponent 2? What are they both equal to?
6, 7, 5, 6.
Okay, so I know my answer must be right then. Great. So we should always know if our answers are correct for these ones. I can always check. Okay, common base between 4 and 32. Any suggestions?
2.
Okay, let's express them with bases of 2. So 4. So I'm using the rule that if I have 2 bases to some exponent, then I know the exponents are equal. Okay, so if I have 3 to the x plus 6 equals 3 to the x to the 4x, I know that those two exponents have to be equal for that to be true. So I'm setting the exponents equal to one another and I'm solving for x. Okay, so bases of 2 over here. How do I express 32 as a base of 2? 2 to the 5? Okay. So I'm just going to simplify the exponents using power rule here. So this will be 2 to the 4x. And then be mindful, this is actually needs to be distributed into that expression there. So it's like 2 to the 5x minus 25. Okay, so now that I have those common bases, I know using the rule above that the exponents must be equal if the bases are equal. And I should be able to solve for x from there. Okay, so we get x equals 25. Okay, you will do a check on here by subbing in 4 to the exponent 2 times 25, and we'll see if that's equal to 32 to the exponent 25 minus 5. Now this is going to give us a pretty huge number. I don't know if our calculators will be able to handle this, but your calculator will probably give it to you in scientific notation. I got 1.267 times 10 to the exponent 30. for 4 to the 50. And then if we do 32 to the 20, I got the same thing. So be good. I moved the 5x over, and I got 4x minus 5x, which is negative x. Any questions? Any other questions for that one? Okay. Can I scroll? All right. So for what we call, basically what we just did is solving exponential equations, so some base with x's in the exponent. When you have powers in your equation with different bases, and it's difficult to write them with the same base, it may be easier to solve by taking the log of both sides and applying the power law of logarithms to remove the variable from the exponent. Okay, so wherever possible, we want to try to create like bases. But if not, I'm going to use log rule, and then I'll use power rule to bring down the exponents in front, and then I'll kind of show you where to go from here. There's some steps over on the right-hand side here. Okay, so 2 and 5, that's a little bit difficult for us to create like bases here. So this is the case where we will just start by taking the log of both sides. And the point of that is basically just so we can get these x's out of the exponents, because it's going to be pretty hard for us to solve if we have x's in our exponents here. So I'm going to bring each of those down in front. Okay, notice that I stuck the exponents kind of in brackets here because technically it's that whole exponent times the log of 2, so the 3x minus 2 all being multiplied by log of 2, and x plus 1, both of those terms being multiplied by the log of 5. So I really encourage you guys write those brackets around your exponents. Okay, usually when I want to solve for x, I need everything with an x on one side and everything without an x on the other side. But these are kind of attached to the logarithms right now. Does anybody have any ideas as to where we could go from here? Now, if you're not sure what to do, you're going to try what you know how to do. What do we usually do if we have something times something else? What's that? Multiply this value into the brackets. Yep. It's a good thought.
That work?
I don't know. Let's see. Okay, now you'll notice this has now allowed me to have 4 individual terms that I can move freely around to the opposite side of the equal sign if I need to. So I'm going to bring everything with an x to one side and everything without an x to the other side. Okay, so just rearranging so that all x's are on one side and all things without x's are on the other side here. Remember to switch the sign of the term as you bring it over. Okay, we're almost there. I need one single x in order to solve for an x. If I have 2 terms with x's, it's going to be very difficult for me to solve. So my suggestion here is that we look at what's common and we take that out. If you notice, both of these terms have a common x. So I'm actually going to remove that x. Okay, common factor, the x. And now we're getting much closer to something that we can actually solve. How do I get the x by itself now? I heard it. Sorry? Divide what? Great. So I'm going to divide out this bracketed part here. And those will cancel. Okay, now there might be one of two things that the question will ask you to do. It will ask you to solve exactly, in which case you'll leave it at this point right here, or it will ask you to solve and round to 3 decimal places. Okay, for our purposes right here, I want to make sure everyone knows how to calculate this. So we're going to solve this one and round to 3 decimal places. The next one, we'll leave it in exact values. So when you enter this into your calculator, I would suggest that you bracket up the top and bracket up the bottom if you want to enter it all in at once. What'd you get? It's up to you. Whatever works for you. Okay, so let's see if we can get this. We should be able to check our answer regardless by subbing back into the original equation.
Got 6.374.
Anyone else get 6.374? Okay, so that looks about what should be the right answer. We'll do a final check here by subbing that in. So 2 to the exponent 3 times 6.374 minus 2, and we'll check if that is equal to 5 to the exponent 6.374 plus 1. These might be off slightly because of the rounding that we did. So let's see what both of these are equal to here. I'm getting 142,638.1133 for this. See if we get the same thing over here.
I got 5, 4, 7, 1, 2, 5 point. No, I didn't get that.
You didn't. This is what I got entering into both sides. So I think we're okay. So this is, again, it's more of an approximate check. These are pretty close. Oh, actually, I actually did get 8 here, not 5. This one was an 8. So it's pretty close. The decimal value part of this is off just slightly. So maybe we would say like approximately equal to, but I think that's enough for us to be confident. What's that? Oh, yeah, I guess it is. Let me just double check. 3 times 6.374 minus 2. Yep, it's off by about 10. Yep, the more you round an exponent, the more your final answers will be off. But I think we can be at least relatively confident. I feel like it shouldn't be this far off though. Hold on, let me just, everyone got this answer though? I know, some rounding exponents though makes it go off quite a bit. You could, if you really wanted to, you can leave a couple more decimals to make sure. Yeah, it's correct. Okay. So for this one, I'm going to have you leave as an exact value. You guys take a couple seconds, and I want you to see if you can solve this one in the video here. Okay, so you guys may notice here that as I was solving, instead of moving all the x's to the left, I moved them to the right. The reason I did this is because usually in my solving process, I try to eliminate as many negatives as possible. What you may have gotten if you moved all the logarithms to the left side with the x's and all the logarithms without the x's to the right side is you would have gotten x log 2 minus x log 3, and then negative log 3 minus log 2. And then once you common factored and divided out, you would have ended up with this. Right? So notice that there's a lot of negatives in here. My answer only has one negative, but you'll see that these are actually the same thing. If I common factor a negative from both of these terms, the top and the bottom, I get positive log 3 minus log 2, and then the negatives actually cancel. So this answer is actually the same as the answer that I got below. Does it really matter? Am I going to be super picky about it? No. But if you have 4 negatives, let's say, in all of your terms, I would say common factor out the negatives from the top and bottom. It's still going to give you the same answer. Pierce?
So does it matter, like say on a test, would one way give you more marks than the other, or
No.
no?
Okay, but I usually just try to eliminate as many negatives as possible. Okay, I can still check this if I actually calculate here, or you could even enter this into your exponents up here. But I can still check by subbing back in. I would just say calculate your logarithm, your logarithmic expression down there, and then sub it in for your exponents.
If I did solve it, would x be equal to negative 1.95?
Let's see here.
That's not correct, if I did that right. So I got the same thing as you, like where the x equals negative log 3 minus log 2 over log 3.
So if you solve, you will get 0.176.
Oh, do it then. So to do it in the calculator, should we do log 3 plus log 2 over log 3 minus log 2?
Yes, but I would say if you're doing it all together, you need to have brackets around the top and bottom in your calculator, or else it won't do order of operations correctly.
Oh, that's what I said.
Okay? All right. The second type of solving exponential type equations would be when I don't have 2 single terms that are set equal to one another. So you'll notice in the ones that we did above, I just have term equals term, and there's no additional terms. When I have multiple terms, especially when I have multiple terms that have kind of like common bases in 2 of them, this solving process is a little bit more involved. What we call these types of exponential equations are exponential equations which are hidden quadratics. So there's not really an obvious method of solving here. The problem is that if I take the log of both sides, I have the log of this entire thing. And then what do I do with the sums that are inside? Okay, when I have sums inside a logarithm, there's not really anything that I can do to get those exponents down or anything like that. So that becomes a bit of a problem if I try to log both sides here. So the process that we're going to do here is we're going to apply either factoring or the quadratic formula to help us, but first we need to get this into a form that we can actually use. Pardon?
The first thing we do is we move the 8 over, right?
What?
The first thing we do is move the 8 over.
Yeah, you can. But firstly, I just want to address this guy right here. Usually we don't like to have bases with negative exponents. Does anyone know what 2 to the negative x is equal to without a negative exponent? 1 over 2 to the x. Okay, so that's what I have here. I've got 1 over 2 to the x.
Can we just put it like 14 in that?
Like over.
Yeah, over instead of 1.
You can, but I don't think you'll need to. Okay, so usually I don't like to solve expressions that have values in the denominator. So we kind of talked about like previously, if I have like different values in denominators, let's say I had something like this. You guys don't have to write this down, but just as an example, how could I remove all those denominators so that I have something that doesn't have fractions in it? What would be the strategy? Alexandra?
Multiply by 4.
Yeah. So I could come through and I could multiply each term by the lowest common denominator. And if I multiply all of those will cancel, and then these will reduce, and I'll be left with something that's a little bit nicer. So if I want to get rid of this denominator, what should I do? 2 to the x, in order to cancel that full thing. So I'm going to come through and I'm going to multiply each thing by 2 to the x here. Okay, and the nice thing is that what's going to happen here is that the 2 to the x's will actually cancel, and I'll just be left with 14.
Could you write it as 2x squared?
Not 2x squared. So when I have common bases, what do I do with the exponents? What are exponent rules telling me to do? I have two common bases that are being multiplied. What do I do with their exponents?
So it's like it would be 4x squared.
No. I add the exponents. So this is 2 to the exponent x plus x. Okay, and I will take Phi suggestion and we'll just move this to the other side as well so that we have it set equal to 0. Jeremy?
How is the 2 to the x in the exponent to the left side, but just multiplying the 8 on the right side?
This is not in the exponent. This is being multiplied.
Oh,
Yeah, sorry, I just didn't have quite enough room to write it next to.
Okay, so you're not multiplying it, you're putting it to the exponent.
I'm multiplying it
So why does
by
that-
each term.
So 2x to the power 2x?
No, 2x times 2x.
So why would that equal to 2x plus x?
Because when I multiply things with common bases, for instance like this, I keep the base and add the exponents. Those are exponent rules, right? Okay, so x plus x is 2x. Okay, we're going to do a little let statement here. I'm going to let 2 to the x equal some variable. Doesn't matter what that is. Oftentimes we use k. Obviously don't use x because we already have an x in there. But yeah, k is good. Y is fine even if you want to use y. Anything other than x. And here's what we're going to do. We're going to replace the two x's, 2 to the exponent x's that we see with k. So I think you guys will start to recognize what this is equal to once you sub in, or how we can solve it rather. So I have 14 plus k squared minus 8k equals 0. And I'm just going to rearrange this a little bit so that we have it in a little bit of a more familiar format. Does anybody recognize this?
It's called quadratic, no, not quadratic, standard form, like quadratic.
Yeah. Okay, so what are my options for solving an expression like this?
We can factor it.
Okay, so I can factor. That's one of the options. I can also, if I can't factor, we can go quadratic formula. So here's our question. We need to think about this. Can we find two things that multiply to 14 and add to negative 8? Anything? 7 and 2, I don't think that's going to make 8. 14 and 1, I think those are the only options, right? Okay, so we've got to go quadratic formula here. Just as a reminder, our nice friend. You guys remember this one?
sadly, yeah.
Don't say sadly, it helps us with a lot of stuff. Okay, so a equals 1, b equals negative 8, c equals 14 here.
Isn't it 2ac?
No, I think you're thinking of the 4ac that's up here. Bottom's just 2a. Okay, so we're going to sub in. All right, I'm going to give you guys a second to calculate that. All right, any answers out there for these ones? Payak, what'd you get?
Like, I fully do, but I just got x equals negative 64 plus or minus the square root of 8 over 2.
Square root of 8 is what we end up with here?
Yeah.
Okay. And then it would be plus on the other side. Okay, that should be enough. Yes, we can simplify the root to like 2 root 2 if we really want to. I'm not super concerned with that. What I am a little bit more concerned with is that we leave this in exact form rather than doing decimal form. So certainly I can express root 8 as 2 root 2, and then I can common factor a 2, and I can reduce the 2's. Many of your calculators may have given you out the answer with this common factored. Sorry. Alexandra?
I got 4.
4?
Like root 4.
Did you? Let's see, 64 minus 4 times 14. I got 8. Maybe you missed something. You can't do this because it's under a root. Also, I can't reduce that from separate terms because of the minus that's in there. Okay, so what your calculators probably gave you was 4 minus root 2 and 4 plus root 2. If you can get here, you can solve it, okay? I'm not super concerned with you getting all the way over to here. It's good practice to be able to do this. But either way, we're going to sub one of these two expressions back into our let statement. So remember, above, we let 2 to the x equal k. I found my k's here. Now I need to find my x's. So I need to sub both of these back into my let statement. Okay, so either 4 minus root 2 is going to equal 2 to the x, or 4 plus root 2 is going to equal 2 to the x. Okay, if you want, you could sub these into your let statement. I would be fine with that. It's really, they're equivalent expressions. They're equal to one another. How do I solve for x now? You guys know how to solve expressions like this?
You square root and square it. Cancel the square root of the other side.
I more so want to get x by itself here. So I think you're going in the reverse direction. Log, we'll solve with log. So if I log both sides here, I can get the x out of the exponent. We'll bring it down. Okay, so same idea on each side here. And then I can get x by itself by just dividing out that log of 2 there. Okay, so really it's the same solving process on both sides. I don't really need to see that on each one here. You could really just solve one and then show a brief solving process for the other one. Okay, so this would be my exact value. If I want to calculate the approximate value, I will calculate this expression, and then I can sub it back in to check my answer. So for our purposes here, I'll show you both, okay? These are the exact solutions. And one thing that we just need to be careful about is that we're not taking the log of a negative here. So I don't think 4 minus the square root of 2 is going to cause that to happen. But if you happen in your solving process to be taking the log of a negative value or even the log of 0, that is not possible. So we would call that thing an extraneous root. So you won't always get two cases like this. You might get to the point where you're testing both cases, but one of them or even both of them could resolve in something that causes us to take the log of a negative, which tells us that that particular root that we found is not a possible root. Okay? If we calculate this, did anybody calculate these and get the decimal values here?
1.371 for the first, and then 2.437 for the other.
Thank you. Okay, these are the answers that you can actually check back into your equation and make sure you get left side equals right side. So if I do 14 to the exponent, or 14 times 2 to the exponent negative 1.371 plus 2 to the exponent 1.371, I should get about 8. Same thing over here. So this would be the approximate solution. It is a bit of a process. The nice thing is that if I get a quadratic that I can factor, I get the k's really quick. Okay, this is the longest possible version of this question that you could have. So if you could do this one, you can do any of them. Okay, and again, we'll check by subbing back in. So I'll let you guys can just do that. I think the next one is factorable, so I'll show you on that one. Okay, so we're going to try one more just so that we're all on the same page with this one. So how can I recognize these? That is always the question I get. So what you're going to look for are 3-term exponential expressions. So what I mean by exponential is like numbers to bases with x's. If it's x's to bases, x's as a base and numbers, that's a polynomial expression. This one's an exponential expression because it's numbers to exponents with x's. So what I'm going to look for are 3 terms. And what you will see is one of 2 things if it's a hidden quadratic question. You will see either one constant term and 2 terms with the same base with exponents of x and negative x. That's like our previous example. Or you'll see something like this where you have a constant, 2 bases that are the same, and exponents of 2x and positive 1x. Okay? So if you see those are the cases where you're going to have to do the let statement and do the hidden quadratic process. Okay? This type is really nice because you can go right into your let statement. Okay? So you're going to do a let. What would I do for my let statement in this case? 3 to the x, yep. Equal some variable. It can be k, it can be s if you want. Not x, anything but x.
X again.
Not x.
X again. It's technically a different variable.
And then we're going to sub in here. So it'll be k squared plus k minus 12 equals 0. Okay, this one's nice because we don't have to do this whole initial process of getting to this point. Okay, so this whole thing that we did up here is not necessary because we already have it in this nice kind of quadratic looking form. Okay, option 1 is always see if you can factor. Claire?
What happened to the 2? Like, you know,
The 2 is there.
The 2? Oh, okay, so you just put x squared.
Yeah.
-4 and 30.
Okay, multiplies to negative 12, adds to positive 1. Did you say negative 4 and 3?
Yeah.
4 and negative 3.
Oh, never mind.
Okay.
See where I go.
So this is super nice because it's a trinomial. When a equals 1, I can sub in the values that I found right away here. What are my k's equal to?
-4 and 3.
There you go. Okay, well, this actually isn't the answer, so I'm not going to box it. But now I just need to sub back into my let statement. So we will have like our case 1, case 2 deal. Case 1 is that 3 to the x equals negative 4. Case 2 is that 3 to the x equals 3. Okay, I think we can solve case 2 without having to use logarithms here. 3 to what exponent equals itself? Okay, so x equals 1 here. Okay, I'm just using common sense for this one. I don't think we need logarithms to help us with this. If I had 3 to the x equals 9, I know x equals 2, right? So this is going to be my case 1 where x equals 2. Now, 3 to what exponent equals negative 4? Not quite sure on that one. Maybe we can use log. Okay, so we'll log both sides here. We can divide out the log of 3. And you should be wondering to yourself right now, or once you sub it into your calculator, why am I getting a math error here?
Because it can't have a logarithm of a negative number.
Okay, no logs of negative numbers. As soon as you see the log of negative 4, this is not possible. Okay? No. What this means is that this produced what we call an extraneous root. So this is not a possible, doesn't give us out a possible solution.
So,
The only solution is x equals 1. Okay, so we call this an extraneous root.
But there is something 3 to the power of x like this.
No? You could try everything under the sun and nothing's going to give you negative 4 if you do 3 to some exponent. 3 to negative exponents just gives you smaller and smaller decimals. Liam?
if you got like an extraneous root on the test, would writing just like x equals NA work as well?
I would like you to identify any extraneous roots that come about from your solving process. So you would just tell me it's an extraneous root. Claire?
How would you get x equals 1? Would you have to still like log it?
So 3 to what exponent equals itself? 1. So you can log it if you want, but you'll get the answer 1 out from that. Jeremy?
Does that mean the answer is just x equals 1?
Yeah, so our only answer is x equals 1. You can check by subbing in. So is 3 to the 1 plus 3 to the 2 minus 12 equal to 0? Well, this is 9 plus 3 minus 12 equals 0, and then we get 0 equals 0. So looks good. Okay? So this is a much shorter version of the question I just showed you. Reason being is that because it's already in a form at the beginning that I'm allowed to just put in the let statement right away. Also, it's factorable, so I don't have to go through the whole quadratic formula solving process. Okay? So if you can do this question, this is the longest possible version of this question that you could have. You could do any of them. It's just this one and this. Or like, for instance, if this quadratic that you got from this type of solving process was not factorable, then you'd do a mix of the two, right? You just wouldn't have to do this like initial process here to get it into this form.
The other factoring methods that we use, why go for that one, that one? Why can't you just do the one where you do the constants of 14?
So
Yeah, where you do the factors of 14.
this produces what we call an irrational root. So it actually, you could try that, but you wouldn't get proper factors.
But would it still be right though? Or?
You wouldn't be able to find a factor.
Wait, so how do you know if it's like one of those that's going to produce that type of?
If I can't find anything that multiplies to 14 and adds to negative 8, then it's going to produce an irrational root from a quadratic.
So,
Yeah.
Wait, an irrational root becomes extraneous?
No, irrational meaning something that looks like this. It's like a decimal value.
But doesn't the one where you have to list the factors of the constant also produce something that you can't multiply and?
That's a rational root, so like 4 over 3, for instance. Irrational means it needs to be expressed with like radicals, basically. Okay, the last thing that I want to show you guys for today is some formulas that we're going to be using in this chapter. These formulas are basically just a more formal version of your y equals a times b to the x. You will get these on the test, so usually what I do is before the question, I'll list these formulas and I'll say use one of these formulas to solve the next question. Pardon? They're similar. Basically, it just explains to you like what you're using each of these for down here. But they already have like basically half and 2 entered in for that usual b value that we have there. So specifically, this guy and this guy are used for half-life questions and doubling questions. This guy can be plus or minus here, depending on if you have percent growth or percent decay. So I'll use minus 1 minus I if I have decay by a percentage, and I'll use 1 plus I if I have growth by a percentage. Now I can also replace this with any growth or decay factor that I have. If it's tripling, I could enter in a 3 here, and the formula works the same way. But these are just kind of like more formal versions of our formulas. A at t represents like future values still. This is called a subscript here, so A with a subscript of 0. Sometimes we call this like A initial or A naught. It just represents the initial value. Okay, and then T here is total time. And H and D, things like this, these are the growth or decay periods. So here, D is the doubling period. Here, capital H is the half-life period. But we already know this already. We've already done X equals total time over growth or decay period. So these are just a little bit more of like formal formulas that we use rather than the one that was introduced to you in grade 10 or 11. So I'll just show you guys how you can utilize the formula. For instance, in example 6, a bacteria culture doubles every 15 minutes. How long will it take for a culture of 20 bacteria to grow to a population of 163,840? Okay, so because this is a doubling question, I'm going to use the doubling formula. And this is basically just like the function notation version of what we have done with the y equals a times b to the x. So A at t, this is going to be my future population at a certain time. So that's going to be 163,840. Initial value is 20 bacteria. Total time, I don't know. That's what the question is asking me. Do we have the doubling period? Okay, 15 minutes. I'm just going to make a little note of that because our final time is going to come out to us in the same unit of measurement that we put in the doubling period as. So our total time will come out in minutes. Okay, someone help us solve this.
Put the 20 over to the other side, and then you could do log what the answer of that is divided by log 2 equal to t over 15, and then just solve.
Okay. So this is very similar to an expression that we had above. I'm curious if we could use potentially common bases to solve this. Is there any value that we can raise 2 to that will equal 8192? I'm just wondering that first before we go and do this whole solving process. Because if we can kind of guess and check here, if I can create common bases, I could actually do this pretty quickly. So 2 to what exponent equals 8192? What'd you find?
13.
Oh, okay. So I can actually solve this guy using common bases. If I am saying 2 to the 13 equals 2 to the exponent t over 15, what do I know about those exponents? They're equal. So 13 must be equal to t over 15. And then I can just multiply the 15 up. That's a little quicker than using log, I think. But can you use log? Absolutely, you can.
Hey, why are
So 13 is equal to t over 15 because they have the same bases. So if I say 2 to the 13 equals 2 to the t over 15, then 13 must be equal to that exponent.
If they didn't have common base, how would you use it?
So we would log both sides, and then we would bring the exponents down and do that whole usual thing.
You're to bring the exponent down with the 15, go with it, or just the t?
T over 15, the whole thing goes down, yeah.
If you were to use log, what would you
So at this point, if I were to use log, I would do, we've done a couple of examples of this in the past, and then I could bring this down, and then I work to get things
do?
moved
Divide by
from
log
the,
two, and then you divide
Yeah.
by log two.
and then multiply up 15. Yep. So can you use this method? Yes, but I think common basis is a little bit quicker here. So 195 minutes is going to be our final answer here, or 3 hours and 3.25 hours, basically. Okay, so we'll just finish that off with an interpretation of our final answer here, using a therefore statement.